So the title of my talk, as you can see here, is Nanostructured Solids, and I will talk about these nanoglasses, and then I hope that I can show to you that these materials may open the door to a new generation of technologies in the same way as we have today's technology, mostly based on crystalline materials, metals, semiconductors, ceramics. They may open the door to a technology based on non-crystalline materials. So what I will do in my talk is to present evidence, first of all, for the fact that the atomic structure of non-crystalline solids is not limited to glasses, as you find it in today's textbook, but that there is a wide spectrum of other non-crystalline solids which exist and which have new properties, so that non-crystalline solids become similar to what we know in crystalline materials like carbon, can be graphite, can be diamond, can be fullerenes and other things, that the same thing exists in non-crystalline solids. And the way, or the reason why we didn't discover it so far, we always prepared it the way a textbook says, take the liquid, quench it. I'll show you new ways, and you will find that there are lots of new structures coming out. And the second thing I want to do is that to show that these non-crystalline solids may open the door to a whole new generation of technologies based on the new properties of these non-crystalline solids, as I said, in the way that crystalline solids are the basis of today's technology. Let me go back in history of materials and technology. When you go back in history of technology and of materials, you will see that we practically, since the Stone Age, then Bronze Age, Iron Age, semiconductor, all the fancy material which we have today, it's mostly crystalline material. And the reason is very simple. In a crystalline material, we can manipulate the defect structure and the chemical structure, and therefore we can manipulate the properties. And I'm showing you here two examples. One is crystalline, single crystal, perfect single crystal palladium, and here is one with many defects in it. And these many defects change the diffusivity by 20 to 30 orders of magnitude at ambient temperature in palladium. 20, 30 orders of magnitude, that's about the growth rate of a tree to the speed of light. Or here, when you go to more complex chemical structures, manipulate the chemical microstructure from pure iron to a complex steel, then you can change the strength by 4 to 5. This is what we can do in crystalline materials. We can manipulate their defect structure and their chemical structure, and then we can change the properties dramatically. And this is essentially the basis of what we do in our modern technology, including, of course, changing the electronic structure. Glassy materials, situation is quite different. You cannot do these things to a glassy material. You inherit essentially the structure, what you get from the melt, which you quench. An example is shown here. This is a two-dimensional silicon dioxide picture, and this is essentially a random network structure, but no defects, no chemical defects, no structural defects. Now, this preference of the crystalline materials has a historical aspect, and this is what I'm trying to get at. When you look at all the solids which we have, essentially we focus on one half, the crystalline ones, and we forget or neglect the non-crystalline ones. And this was the starting point of the whole work I'm talking about here, if we would succeed to utilize the non-crystalline solids, do the same thing with them, then of course we could repeat essentially what has been done in the last 10, 15,000 years with crystalline solids and get a new approach to solid materials and of course to technology.